Hi, calculus students. This is lesson 6.8. We're going to be looking at antiderivatives, indefinite integrals, and the fundamental theorem of calculus, and hopefully try to clear up some things you may have been confused about in the last few AP daily videos. So I'm going to share my screen and start the presentation. And our first slide starts with a warm-up. So when it comes up, you might want to pause the screen and give these problems a try, and then we'll come back. All right, welcome back. Hopefully you had a chance to try these problems. There's some true false questions. If it's false, you need to explain why or why not, or why, and give an example that shows why it's false. So in this first one, it states that the integral from a to b of the quantity f of x plus g of x dx can be written as the integral from a to b of f of x dx plus the integral from a to b of g of x dx. That's certainly true. All right, that's one of our basic properties of integrals. Number two, the value from a to b of f of x dx must be positive. Hopefully you said that one was false. We've certainly had a few cases of this. Let's say I have some graph here, and I'll make this A, and this is B. And we might have some semicircle or something that lies underneath the x-axis here. And remember, if we're trying to integrate something that lies below the x-axis, we end up with a negative value for our integral. So that one's false. On 3, it says if the integral from a to b of f of x dx is greater than 0, then the function is non-negative for all x in a, b. We've seen some of these as well. So it could be, we could get an answer. Let's just say this is A and this is B. All right, we could certainly end up with a positive answer if we were trying to integrate something like this. But as you can see, our answer comes out to be positive because the positive or the above the x-axis values outweigh the below, but the function is not non-negative. In other words, it's not always above the x-axis. So this one is also false. All right, let's look at what we're doing today. We're doing antiderivatives and definite integrals, fundamental theorem of calculus parts 1 and 2. I'm Mary Bird. I teach at Sandpoint High School in Sandpoint, Idaho. All right, what are we going to learn? We're going to learn that the area under a curve can be found using a definite integral. We're going to learn that antiderivatives can be found for indefinite integrals, and that the fundamental theorem of calculus shows us the relationship between the area under a curve and definite integrals. All right, so antiderivatives, indefinite integrals, you had these before. This was the first thing we looked at right before spring break. I kind of gave you a little intro worksheet. The expression of the integral f of x dx is read as the antiderivative of f with respect to x. Integration is the inverse of deriving, or the inverse of differentiation. For example, if we have a function, we've got a weird extra equals in there. If we have the integral f of x dx is equal to f of x plus c, then we could take the derivative of both sides and just end up with our original f of x. These things undo each other. And that equal shouldn't be there, just so you know. Thought I changed that. We have all of these integration rules. These are on your worksheet along with the different properties. This one just talks about if you have some, just a derivative here, or excuse me, just an integral, that's variable. It could be like x or something plus c. In all of these cases, most of the places, the u can be replaced with an x. The reason they use u is because, as we'll see later in this unit, we have the chain rule, and so the u represents some function. This one is written as du over u. It's the same thing as 1 over u du. The antiderivative of that would be the natural log. You'll notice they put this absolute value sign around this whenever they're working with natural logs, because if you recall, a natural log function is only defined, its domain is values of x greater than 0. So you'll see that a lot. E, of course, is our friend. This one we haven't talked about too much, but this is, it'd be like if you had the antiderivative of 3 to the x would be 1 over the natural log of 3 times 3 to the x. Here are all our trig functions. These are the ones you'll see most often. You don't see a lot of the other I don't know, cotangent and those sort of things. We'll see those integrals later. And then these, we do have our arctangents, arcsines, and arcsecants. I noticed they didn't put arc cosine in here, but you could also have arc cos. Remember the difference between arc cosine and arcsine is that negative one term up here. And notice they put the du on top. It could certainly be at the side with a 1 on top. Same thing here and here. All right, so we're going to just do a little practice with, it says find the definite integral, but these are not definite integrals. These are indefinite integrals. I'm going to change that right now. That's crazy. All right, find the indefinite integral. And what's the difference between an indefinite integral and a regular integral? Indefinite means there's no limits of integration. So these are the ones we're always going to have to remember to put plus c. All right. A definite integral has limits of integration, and we can get an actual answer. But in this case, since we don't know what that constant is, these are referred to as indefinite integrals. All right, so this one, I'm trying to undo x to the fourth. This is the general power rule. I need to add 1 here, and then I also need to add 1, like 4 plus 1 in the denominator. So this would be 1/5 x to the 5th plus c. And you also could write that as x to the 5th over 5 plus c, same thing. This one, before I try to integrate it, I'm going to rewrite this integral as x to the -1/2 dx. It's a little easier to see that power rule undone here. So if I add 1 to -1/2, that'd be -1/2 plus 2/2 is 1/2. I have the same thing in the denominator. So I'd have x to the 1/2 over 1/2, right? Remember, I'm climbing up. So that would turn into 2x to the 1/2 power, right? Remember, if you divide by a fraction, you're going to flip, plus c, or you could write it as 2 square root of x plus c. And it did say here to check your work using differentiation. If I did this here, I'd notice 5 times the 5th is 1, x to the 4th, that's what we had. If I did that here, half of 2 is 1, 1x, subtract 1 here, 1x to the -1/2, that's what I have. This one, let's see, I can't see the problem because I've got my little picture of me in the way. All righty, let's look at this one. All right, this time I have to climb up one that's cubed. So this is looking like a nice 2x cubed. This would be, let's see here, 5/2 x to the 2nd minus 3x plus c. Remember to check your work by differentiating. 3 times 2 is 6x squared. 2 times 5/2 is 5x. Derivative of -3x is -3, and the derivative of a constant is 0. All right, this is one. We have that fraction with just an x in the denominator. So this should be 3 ln. And again, we're going to put the absolute value of x just to be sure that we're not going to get any negative x values in there. All right, this time, whenever you see a fraction, your options are, is it a natural log? In this case, nope. This, hopefully you recognize that this is arctan. So the antiderivative would be the arctan of x plus c. Nothing fancy there. There's nothing strange being input here. We'll have some later, again, with the chain rule. This one, remember, e is our friend. The antiderivative of this is 5e to the x plus c. All right, let's look at our next slide. All right, the fundamental theorem of calculus part 1 says if f is continuous on the closed interval and f is an antiderivative on the interval, then the integral from a to b of f of x dx, if I find the antiderivative, we call that this big F, I can evaluate that as f of b minus f of a. And we've done a few of these, and hopefully you saw these in the, I think it was the six videos that Mark did. Hopefully you saw that. So let's look at an example. It says find the area of the region bound by the curve y equals negative x squared plus 3x and the x-axis. Sketch a graph. All right, so always a good idea. I can see this is going to be a parabola. Oop, let me go back. I didn't have my pen there here. Switch colors. All right, so I want to know what this looks like. Namely, I'd like my x-intercepts. So I'm going to factor out a negative x here. And that's going to give me x minus 3. All right, so if I set that equal to 0, it looks like I'm going to have x-intercepts at 0 and 3. So I'm trying to evaluate 1, 2, 3. I have my parabola here. All right, I could find that actual at highest point there, right? Remember, set the derivative equal to 0. I'd have negative 2x plus 3 if I set that equal to 0. My x coordinate of my vertex here would be negative 3 halves. Plug it in, find your y. So I am trying to find the area of this region. All right, the nice thing about the fundamental theorem of calculus, that says you want to know the area of that, set up an integral from, in this case, we're going from 0 to 3. I put in the function I'm trying to integrate. I find the antiderivative and I evaluate it at 3 and then subtract the value at 0. So antiderivative of negative x squared would be negative 1/3 x cubed. Antiderivative of 3x would be a positive 3 halves x squared. And I'm going to evaluate that from 0 to 3. And I always read from bottom to top. You're going from 0 to 3. So the first time I do this, I put 3 in for x. Next time through, I put 0 in for x, and I subtract those two. So 3 cubed is 27 times negative 1/3 would be negative 9. And here we have 3 squared is 9 times 3 is 27 halves. Minus, and if I notice this one, and it's nice when it's a polynomial and you have a 0, 0, 0, this is just going to be 0. Zeros are really nice when you have it as a limit of integration. You just need to be careful if it's something like, oh, there's like x minus 5 or something, then you can still evaluate with the 0, or if you had cosine here or sine here, you could still evaluate it at 0. So be careful, it doesn't always go away, it just does in this case with this nice polynomial. So I'm just left evaluating this part. Negative 9 is the same thing as negative 18 halves plus 27 halves. Should leave me with an answer of 9 halves is the area under the curve. If you had done a left Riemann sum or a right Riemann sum, you would have come close to that. But the fundamental theorem of calculus says that the integral finds this exact value here. All right, let's look at our next one. This time we have average value. It was talked about briefly in one of the videos. So if I'm trying to find the average value of this function on the interval, it's the same way we just did that last problem. I'm going to set up my integral. I know I'm going from negative 3 to 0. And when you have average value, you are going to multiply it times 1 over, come on, pen, 1 over b minus a, in this case, 1 over 0 minus negative 3, right, which would be 1/3. So I have 1/3 times the integral from negative 3 to 0. Our function is 3x squared plus 4x dx. And so we have 1/3 times the antiderivative of this, which would be x cubed plus 2x squared, right? You can always rewind, go back, try those on your own. And this time we're going from negative 3 to 0. All right, so I'm going to keep simplifying. I still have my 1/3. This time I'm plugging 0 in first. So 0 cubed plus 2 times 0 squared, that's going to be a 0. Minus, now I have to plug my -3 in. -3 cubed is -27. Plus, -3 squared is 9 times 2 is 18. Then if I simplify that, -27 plus 18 is -9. This makes it +9. So I have 1/3 times 9. So the average value of this function on the interval -3 to 0 is 3. All right, fundamental theorem of calculus part 2. Grab my pen again here. This time it says if you have some limit of integration that is itself a function, and if I take the derivative of that, it's the same thing as evaluating it just at f of x. All right, I believe that the directions, let me look at them here on example 4. It asked you to integrate to find f as a function of x and demonstrate the second fundamental theorem of calculus by differentiating your results. Okay, so suppose I didn't know the second fundamental theorem of calculus. I might look at this problem and go, all right, I'm going to find the antiderivative of this. So we have the square root of t, which I can rewrite this integral as the integral from 4 to x of t to the 1/2 dt. I'm going to find the antiderivative of that. So 1/2 plus 1 would be 1/2 plus 2/2 is 3/2. So this is 2/3 t to the 3/2. And if you're not sure of that, you can always derive it, right? Take the derivative, see if I'm right. And we're evaluating that from 4 to x. So first I plug an x in there and I'd have 2/3 x to the 3/2 minus 2/3 times 4 to the 3/2. So this one stays as 2/3 x to the 3/2. And this one, let's see, bottom is the root, so square root of 4 is 2, 2 cubed is 8, 8 times 2 is 16, so 16/3. All right, so that's what we have our f is equal to. And it says to check that the fundamental theorem of calculus works, take the derivative of this. So let's see, f prime of x would be equal to, let's see, 3/2 times 2/3 is 1. So I have 1x to the 3/2 minus 1, 3/2 minus 2/2 is 1/2. So let's, and then the derivative of 16/3 is 0, right? It's a constant, so that's what I get. So let's see if that's what I get by taking the derivative of both sides here. So derivative of f is f prime. And according to the second fundamental theorem of calculus, if I take that derivative, it's the same as replacing whatever that t is with an x. And if you look, that's what we had. Square root of x is the same as x to the 1/2. So, and when you see these on the AP exam, they're not going to give you ones like this that you could just evaluate. They're going to give you some crazy function which requires that you know the second fundamental theorem of calculus, that you know to plug this x in here. All right, if this limit of integration is itself a function, you will have to use the chain rule. So in addition to plugging the x in, you will also have to do the chain rule for whatever this is. If I do that on this problem, you can see the chain rule derivative of x is just 1. So this is square root of x times 1, or just square root of x. All right, so we have one of those here. This is another example of the second fundamental theorem of calculus. This is asking us to find f prime. So remember, if I take the derivative of this, I can plug this in everywhere I see my t, but then I have to use the chain rule. So it's going to be equal to 1 over x squared is what I'm replacing t with, and it's still cubed. And then I take the derivative of x squared, which is 2x. All right, so I'm going to keep simplifying. That gives me 2x over x to the 6th. And my final answer would be 2 over x to the 5th. And that's what f prime is equal to. All right, this is another case. This is one of those where we have the alternative form of the second fundamental theorem. So this time we have a derivative. F prime of x is equal to sine of x squared. We know the value f of 2 is -5, and we're trying to find f of 1. So I'm going to start this. I know this is the derivative. So I'm going to see, grab my pen here. Let's go back to this. Let's see if I can scroll all the way down here. We're on this one. All right. All right, so let's go back, grab the pen. We have the integral. Looks like we're going from 1 to 2, right? We're trying to find f of 1. So 1 to 2 of our function, sine of x squared dx, right? And by the second fundamental theorem of calculus, this should be equal to, this is our f of x, right? If f prime is equal to the inside, then f of x is equal to the integral. And that would be equal to f of 2 minus f of 1, right? Antiderivative evaluated at these limits of integration. So we know here, let's just rewrite this. 1 to 2 sine of x squared dx is equal to, and we know this value, f of 2 is -5. And we are trying to find f of 1. All right, so I'm going to rewrite this. I'm going to move my f of 1 to the other side. So f of 1 would be equal to -5 minus this integral from 1 to 2 of sine of x squared. And if you haven't noticed, this is one of those cases I was just talking about that they give you something you can't evaluate by hand. We're going to have to use a calculator for this one. So grab your calculator, and I'm going to switch over to, I made like a little video of the calculator because I didn't have any way to show it here unless I like held it up on the screen. It'd be really hard to see. So I'm going to stop this share here. So make sure you have this written down, -5 minus the integral from 1 to 2 of sine of x squared dx. All right. And I'm going to do a different share screen here. I'm going to go to my fun little calculator video. Let's see if it'll show up. Maybe. Well, let me share that. I don't know if you guys can see this. I hope you can. Move that out of the way. Hey, there's me. All right, so let's look at the video of what's going on here. So I have my calculator and I go to calculate and I go down to, I'll just let the video show what it does here. All right, so that's it for a video. Thanks for joining me. I hope this helped clarify some stuff. You can ask questions or send me an email. Good luck, and don't forget to do the assignment. See you in class.